Question 10, Part A. A circular pizza of radius 20 centimeters is cut into sectors. Each sector is to be placed on a circular plate that is just large enough to contain that sector. Part 1. A sector of pizza is cut where the angle theta at its center satisfies theta greater than 0 and less than or equal to pi over 2. It is placed on a circular plate of radius r centimeters and center C as shown below. Show that r equals 10 sec theta over 2 for theta greater than 0 and less than or equal to pi over 2. Consider triangle ADC. Now triangle ADC is isosceles since AC equals DC, which equals r, and r is the radius of the circle. Hence AB is equal to BD, which equals to 10 centimeters. In right angle triangle ABC, and there's the right angle there, angle ABC is equal to 90 degrees, and that's given. And using regular right angle trigonometry, cos of theta over 2 is equal to adjacent over hypotenuse, so AB being the adjacent side and AC being the hypotenuse. We get cos of theta over 2 is equal to 10 over r. Multiplying both sides of the equation by r, we get r times cos theta over 2 is equal to 10. Dividing both sides of the equation by cos theta over 2, we get r is equal to 10 divided by cos theta over 2, or 10 over cos theta over 2, which equals 10 sec theta over 2. Therefore, r equals 10 sec theta over 2 for theta greater than 0 and less than or equal to pi over 2 as required. Part 2. Another sector of pizza is cut where the angle theta at its center satisfies theta greater than pi over 2 and less than pi. This sector of pizza is placed on a circular plate as shown below. Again, we let the radius of the plate be r centimeters and we let the center be C. Show that r equals 20 sine theta over 2 for theta greater than pi over 2 and less than pi. Consider either of the two right angle triangles. Now both right angle triangles are congruent since corresponding sides are equal in length. Now it's a right angle triangle, so we can apply regular right angle trigonometry. So we have an opposite side and a hypotenuse, and opposite over hypotenuse is represented by the sine ratio. So sine theta over 2 is equal to opposite over hypotenuse, and we can write that as an equation. So sine theta over 2 is equal to r over 20. Multiplying both sides by 20 to make r the subject, we get 20 times sine theta over 2 is equal to r. And then rewriting it with the subject on the left-hand side, we get r is equal to 20 sine theta over 2 for theta greater than pi over 2 and less than pi as required. Part 3. Sketch the graph of r as defined by the equations in parts 1 and 2 for theta greater than 0 and less than pi. This part is asking us to graph the piecewise function f of theta, which equals r, which equals 10 sec theta over 2 for theta greater than 0 and less than or equal to pi over 2, and f of theta equals r, which equals 20 sine theta over 2 for theta greater than pi over 2 and less than pi. Now, in order to help us graph this piecewise function, it helps to recall the graphs of the base curves r equals sec theta and r equals sine theta. So here is the graph of r equals sec theta. Notice the vertical asymptotes at theta equals pi over 2 and 3 pi over 2. And also the y-intercept here of 1. And also notice that the maximum value on this branch of r equals sec theta is -1. And here is the graph of the base curve r equals sine theta. Notice the peak here at +1 when theta is equal to pi over 2, and the minimum value here, or the trough, of -1 when theta is equal to 3 pi over 2. Now, both graphs have been dilated vertically and horizontally, stretched, not compressed. Here is a sketch of the graph of the piecewise function r equals f of theta. Now, from theta between 0 and pi over 2, this is the function 10 sec theta over 2. And for values of theta between pi over 2 and pi, this is the function 20 sine theta over 2. Notice the open circles here and here. Also notice this point here, where theta is equal to pi over 2, the value of r is identical for 10 sec theta over 2 and for 20 sine theta over 2, which is 10 root 2. So this is the joining point, or the connection point between the two piecewise function. And I've tried as much as possible to draw the function as a continuous curve, not necessarily smooth, but certainly continuous.